For more information, please visit our website at DarkCybernetics.com. This is DarkCybernetics, Data Structures, Abstract Data Types. Follow on our free course documentation. In this video, we will discuss ADT, or Abstract Data Types, and how to distinguish them from a data structure. A data structure is a particular way to store, manage, and access data in an efficient way using some type of system. In this case, an abstract data type refers to what would this refer to? It will refer to a mathematical model Okay, so we're saying that an abstract data type refers to some type of mathematical model that for a certain degree or class of data structure. So it's supposed to be two S's on this class here on the end, but we'll keep going. A class of data structure that have similar behavior. So we're saying that an abstract data type is a mathematical model for a certain class of data structure that has or have similar behavior. Okay. Right. And we can say that there are two types. We have to distinguish between the abstract data types, or ADT, from our DS, which is our data structure. So let's draw a diagram for that. So there's a DS here is a data structure, and an abstract data types, and we have to distinguish the two. So let's draw a line. So we've defined what an abstract data type is. We're saying that it's a mathematical model for certain degrees, types of behaviors. And so let's distinguish that behavior. For an abstract data type, we can say that an abstract data type is what we call the mathematical or logical description of the data, and we can believe that, and this is at the logical level. And this is what we refer to as the implementation level for the data structure. The data structure itself is the implementation. Suppose it was an array or some type of user-defined data type. That's what we're referring to here. It's a user-defined data type. It is a class, or it is, we can have a logical array, or we can have this is really language dependent, right? So we're saying that this is you're supposed to use a language like C++ or Java to represent the implementation of our system where we store it, and we would use math, of course, to execute the abstract data types. Alright, that sounds reasonable. We have math to make sure it's efficient, and we have a programming language to implement the systems. Alright, so let's divide these two up into two sections. So we know that we have to do math for one region, and we have to use a programming language to implement the other portions of the coding system. Okay, so let's work on the implementation portion, or the data structure portion. And we can say that when we code something, and suppose we were using some type of signed, what's signed on the computer? Signed magnitudinal. Okay, magnitudinal. Some type of some signed magnitudinal integer value, or representation for our system or our program, for a number, for an integer value, instead of values of real numbers. real numbers can represent positive and negative values, and we would have to have some type of integer value. We have to define the type, and then we would say we had a variable, whatever the variable was. Suppose it was number. We can use NUM to represent number, and we have to specify the value for it, and this value would have to be negative or positive for, this is what we would call a primitive type, just a variable by itself, and that variable could also be negative. Okay. Seems simple enough, right? We have an integer value, it can be a sign, magnitude, representation, but over in the other category, we need a logical representation of this operation. It really depends on the data structure. If we use different types of data structures or data types, we need to in turn differentiate the difference between the logical description and we can, for a logical activity, we can define it by its definition for what this type of data structure was, and we need some type of what, if we can define it, we need to define it by, of course, its operations, because the operations for each data structure is different. So if we use an array or a linked list or something like a stack or a queue, we can define it by its two attributes. So if we had some type of information here, we could say that if we had a stack or a sequence, right, it would have two operations. It would have a definition and have its operations. And if we had another type of or something like a list, we would define it by its operations. It has operated. It can do these things. It's supposed to can copy, paste, or what have you. Okay. Let's use some color maybe for this one. Suppose we still had we're still going over the same material. We have a data structure. Okay, we have a data structure here, and there's some other information we need to think about when we use data structures. We have an array. There are certain operations that arrays can do, and each we start at 0 to n minus 1. And if we use a linked list, depending on the degree of the linked list, it could be a singly linked list. In a single linked list, you can only go forward in the linked list. All right. Usually when we make a linked list, we have boxes, and then they always point to the next one. This data member, and then it points to the next, and it usually points to null if it's not unassigned to somewhere. Okay, this would be a data structure here. We'll talk about that later. And really, depending on the type of language we use, we could not do all the same features. So if we were using C++, in C++ we can access memory addresses. So that might be reasonable, right? If we had to use pointers and reference memory addresses, memory locations on one area, this may be a reason why we pick certain data structures. We need direct access to the hardware, or direct access to certain features, maybe just language specific. If we're using some other more higher languages, higher level, more human-like languages, we may have a problem with this. So this is one of the reasons why we have to understand the difference between one data structure and another. If we had something like, let's make a box here for something like Java. Java cannot reference memory addresses, so this would be an automatic problem. So this would alleviate one concern. So we could reduce the language from our pool of information. So if we had to get rid of that language, we could just move over to something else. So here in the abstract data types category, there's information we need to understand as well. That when we have a logical okay, picture of data or data and we describe, we have a description of operations so we have an abstract data type. We can have a logical picture of data and descriptions of the operations to manipulate the component elements in data. So we're saying that in the abstract data type region we can have a logical picture of data and descriptions of operations to manipulate the component elements, and for our data structures we have to know which data structure we would intend to use and what drawbacks we would need or have available when we pick a language to use for a particular project. And this is half really the battle when we pick data structures and we study data structures. Will data structures make you a better programmer? In some cases, no. But it will help you when you have some type of interview or some type of quiz. You'll be a bit more prepared about what to say or what to do in certain situations. And suppose we want to know about, there's different types of data structures. Well, data structure types come in different categories, and this is not hard to understand that there are primitive. Let's write it up here. Primitive. Right? Primitive. We think primal, and these are the very basics that we can have for our data types of data structures. And there are non-primitive. And when we say the difference between primitive, non-primitive, primitive are really based on the machine architecture, and non-primitive is generally referred to as user-defined data structures. And these are a bit different based on the language. There are hundreds of different languages, and when we say that we have a primitive, what we're referring to being primitive is we're saying that we have integer values, and we're saying that there are real numbers, and we're saying that there are character data, and then we're saying that there is perhaps Boolean values. And for our data structures, we're saying that there are non-primitives, being that they're user-defined. We're saying that there are linear, right? They're homogeneous data structures, right? And we're saying those the linear homogeneous data structures are information pieces like the array, right? We use arrays. And there are pieces such as linked lists, right? The arrays, linked lists, and there would also be, of course, stacks and queues, right? First in, first out, last in, first out. Well, that may be backwards, but we will get to it later, right? So if you can traverse information. We can go back and forth with information. If you think about going to a restaurant, there's plates and cups. And the first plate you pick up is the last plate they put down, based on if it's a stack or it's a queue. Arrays could be like a database, or a linked list could be like files and folder records. And we talk about the what we call the tree and graph notations. Suppose you're making a program for a chess game, or had to return board states. We use some type of tree and graph notation here. This is very important for programmers, anyone new to programming, that understand the concepts of arrays, how to use linked lists for nodes, the difference between a stack and a queue, how to manipulate trees and graphs in a program for like Dijkstra's algorithm, or when to use integers, real values, characters, and booleans. So this is very important, a very important concept, at least for new programmers. This is really important for classes such as algorithms, where we have to understand which data structure to use when we need to have an efficient algorithm. And we say that an algorithm is a logical step-by-step process for solving a problem in a finite amount of time in legal computational steps. But for this area, we are discussing data structures, and data structures have almost all almost all programming languages have user-defined, have these primitive, not really user-defined, most of them have the, almost all programming languages have what? They have primitives. They have primitive, right? They have these primitive data types we can manipulate. So if you're using different hardware, we know that a computer has different hardware. So it has nowadays a computer has several CPUs, it has memory, it has some bus input and output ports, and it has some way to store memory, some type of contiguous memory. And when we go to the computer to write programs, we need to know the difference between using what data type. Suppose we want to have a reflection of the hardware, right? Our primitives really, and data types, things generally are a reflection of what type of system we have. If you had a different type of computer, or a different type of if you use an embedded system, like many airplanes and things use embedded systems because they have a microcontroller, and if you have which is really beyond this course, but if you're flying a plane or something, the information that it may be a bit different nowadays than it was years ago. If they're implementing the material, and you want to access, suppose you had something like floating points, and this is really a problem that happens when you pick data structures for things, and when you cannot use data structures for a system. And suppose you want to implement something like floating point values for CPUs, but suppose your system, you were deciding to program this system, the system, like the CPU itself, may not support the floating point values. So we can say that the CPU does not support floating points. It does not support floating points. So that will be a problem for your data structure, or your language. Okay, that's awesome. So we can say that almost all programming languages have primitive data types, and this is generally a reflection of the capacity of the hardware, or the capabilities of the hardware. And we say that for one problem we have is that certain CPUs do not support floating points, or CPUs do not support floating points at all. Okay. Moving on to our next item, we are going to discuss different types of data types. And again, here we'll draw a different diagram. So we have a data type, and for the data type, we're going to say that there are certain parts of data type that, of course, again, are, user-defined. It's right up here. This side will be things that are generally user-defined. We talked about before. The parts, or if we different algorithm-based implementations. There's algorithm-based implementations, and before there are machine-level implementations for a language like arrays. We can have a logical linked list, but on the computer system, we need to know which parts are the machine instruction level information. Like we know what variables you can have. Like you may have a programming language that does not have Boolean values, like C and C++. Maybe that's the difference. They may have User-defined, maybe you think for the lower, pretty much language-specific areas, such as class and structs. We of course have here again primitives. We have primitives here. Alright, we have primitives on this side, and of course we have booleans, and then we, from the primitives, the other thing it would extend into are of course the integer values. And we have primitives, boolean. Some languages do not support boolean values, and some languages read this is numeric information. We have to really define what we're talking about, because in some languages even the characters themselves are read as numeric values. So it's the primitives, the numeric, and this information can be what? It is integer, right? So if it's primitive, it's numeric, it can be integer. We're referring to machine level architecture. And this information can be, of course, what, byte? It could be 8 bits or a byte. It can be short, it could be 4 bits or 4 bytes. It could be a bit, and it could be long. It could be just a regular integer value. Okay. We're referring to a data type here. And this also could be a character, and that could be just a string, right? An individual character in a string, not the string itself. And of course on the other side, it could be user-defined, so in turn it would be non-primitive. Non-primitive, we have to abbreviate here. Maybe we'll run out of space. Maybe. Can we do it? Alright. It's non-primitive on this side. And those would extend into the user-defined data types. And this is what a class for C++ is. C++ classes are supported in Java as well. And we can have arrays, of course, in many languages. And we can also have strings, right? That may not be prevalent in some languages, but we know we can have it here in C++. And we can have an interface, and interfaces may be supported by this language. Alright, and so there are other extensions of this that we can have based on language. They could be tuples and classes and functions, and these are pretty much user-defined part of the language. And we have bytes and short. We have primitives, right? And we've seen that these character types. We have bytes, shorts, integers, and longs. And we have chars, and we assign a variable. We can have booleans for the language, and let's write it here. But there are no booleans in the basic C language. There's no booleans in C language, not in C, but they are in C++. Okay, C++. Let's write 2 pluses here. Okay, but they are okay in C. And here, difference between C++ and C is that there are no classes in C, but instead they have what we call structs, and those structs are always public, but in classes we can have private. Okay, this is okay in C++. And for more information, please visit our website at DarkCybernetics.com.